I am Sheikh Ashidur Rahman, Assistant Professor, Department of Electrical and Electronic Engineering. So today I am going to deliver my lecture about power flow solution. In another way, it can be called load flow studies. So in this lecture, actually at first we have to know something, that is if this is a synchronous generator or alternator, then it can be produce power, and this power will be delivered to the connected bus. So now if there will be some demand of this particular bus, then at first the power delivered from the generator will supply the demand of the load. After that, the rest of the power will be delivered from this bus to the other connected bus. So if PGI is the schedule power being generated at bus I, that is the generated power, and PDI is the demand power of this particular bus, that is the bus number I, then the net schedule power being injected from the particular bus I to the other bus should be generated power minus the demand of this bus. So this is the equation of schedule power or the transmitted power from particular bus to the other buses or other connected buses. So the equation should be schedule power or the injected power is equal to the generated power minus the demand of the particular bus in which bus the generator is being connected. Now this equation is true for the real power as well as for the reactive power. So figure B is the replica of figure A, which is just introduced for the reactive power. So if we can calculate the net injected power from particular bus I to other buses for reactive power case, the equation should be QG, that is the generated reactive power, minus the QD, that is the demand of reactive power, and that should be the scheduled reactive power being injected from bus I to the other buses. Now if we have to calculate the power mismatch equation, then the power mismatch means the scheduled power minus the calculated power. So it should be 0, because if it is 0, it means that there is no power mismatch. The power which should have been injected from particular bus to other buses and the calculated power, it is also represent the same value. So the power mismatch is equal to 0. That is the power mismatch del Pi, that is the real power mismatch, is equal to the schedule power that is injected from particular bus I to other buses minus the calculated schedule power of this particular bus I. So if this subtraction result is 0, it means that the power mismatch will be 0 or the power mismatch is 0. And if there would be some value, it means that the power mismatch is not 0, there will be some error. So this is similar for reactive power. Now, so why we calculate this power flow solution, or why we use these load flow studies actually? Because the power system is interconnected power system, different types of buses are connected together. So if we want to calculate the individual bus voltage and angle, then we have to calculate this through a process, and that is the load flow studies. Because if we want to know how much power is being generated from a particular generator and how much power have been consumed by the load and what is the line losses actually, it means that some power should have lost due to the line losses, due to the resistance or reactance. So how would be the losses through this line. So this is the whole power flow solution. So the generated power, the consumed power, and the losses, all we can calculate by using the load flow solution or the power flow solution. And now to calculate the all types of power, it means that the consumed power or the generated power or the line losses, at first we have to calculate the individual bus voltage and angle. And to find out the individual bus voltage and angle, we have to use the load flow study. Load flow study is a process to solve the nonlinear algebraic equation. By using this process, we can calculate the individual bus voltage and the angle also. Now, in the previous page, actually, if we want to develop the power equation or the complex power equation for interconnected power system, then we can form this equation by using this process. Actually, at first, the Y bus matrix or the bus admittance matrix is a complex matrix which contains the real part and imaginary part. So we can write down this by from this particular polar format, that is the magnitude of the element of Y bus matrix, and there should have been an angle actually. So Yij, it represent I is the row number and J is the column number. So if I is equal to 1 and J is equal to 3, that means that Y13. So this is the magnitude of Y bus matrix element, first row third column element, that is Y13, and this is the theta. Theta is the angle, so that is theta 13. It means that the angle of this particular Y bus matrix element or the bus admittance matrix element. So you can represent a Y bus matrix element look like this, that is a real part and an imaginary part. Now, this is a complex number, so the voltage or the bus voltage should have also a complex format, that is a magnitude of bus voltage and that is the angle of a particular bus voltage, and that is represented by delta. Now the current equation actually, so if we can calculate the current of an interconnected power system, at first we have to identify the bus number or for which bus we have to calculate the current. So if in general format we assume that our bus number is I, that is the alphabetic number I, then this is the current notation capital I, and this is the suffix I, that is mean the bus number. So if we calculate the current injected from bus I, that is the equation should be summation small n 1 to capital N, that the Y bus matrix element capital Y I N into Vn, that is the bus voltage, because we know the equation of current should be admittance into voltage. I is equal to Y into V, that is the admittance into voltage. So now this small n will be start from 1, and this is capital N represent the total number of bus of the system. So if a system contains 5 bus, then capital N should be 5. So there should be 5 term, that is 1 to 5. There should be 5 individual summation term of the current equation. If the capital N is equal to 10, it means that in the particular power system there is 10 buses, then the current term should be 10 individual summation terms. So there should be 10 particular term of the current equation. So if I just elaborate this equation, then if this is a 5 bus power system and we want to calculate the current for bus 2, then that should be I2, that is suffix I, this value is equal to 2. So the current injected from bus 2 equation should be I2 is equal to small n is 1. So we have to start our calculation from 1. So capital YIN, I is equal to 2, because we calculate the current injected from bus 2. So Y21, because small n is start from 1. So Y21 into V1, that is the bus voltage of bus number 1. Next, the second term should be n is now 1 plus 1, that is 2. So the second term should be y2 2 into v2 plus the third term should be n is now increased from 2 to 3. So y2 3 into v3 plus fourth term should be y2 4 into v4 plus the fifth term should be y2 5 into v5. So uh, if I extend this current equation in a particular format, then if so so the current equation should be uh, I and small I. So this is the notation actually. So like this. Now the current equation should be if I is equal to 2. So we have to consider at first if small I is equal to 2. It means that we have to small I is equal to 2. Well, there is a problem in my keyboard like this. So if this small I, so that is the small I, so small I is equal to 2 and the capital N is equal to 5. It means that there are 5 bus power system. So if we want to calculate the current of bus 2, then that should be I2 because small I is 2. So we have to calculate the current for bus 2. Then the equation should be capital Y, that is capital Y IN into VL. So N start from 1. So the equation should be Y21 into V1 plus next y22 into v2 plus next y23 into v3 plus next y24 into v4 plus the final equation should be y25 into v5. So this is our equation. So this is the current equation for bus 2 if the power system contains 5 buses, and then the current equation for bus 2 is given here. So if we finally modify this equation and more clear view, then the equation should look like this. So this is the final format equation. So if we want to consider that this is our current equation, so particular bus 2, and if the power system contains 5 buses, then equation should be I2 is equal to y21 into v1 plus y22 into v2 plus y23 into v3 plus y24 into v4 plus y25 into v5. So if we use this equation for bus 3, that is I is now 3 and total number of bus is 5, then this 2 should be 3 and the equation will be changed y y31 into v1, y32 into v2, y33 into v3, y34 into v4, and y35 into v5. And now, if we want to write the current equation for bus 5, then I is equal to 5, then there should be 5, and now this should be 5-1 V1, 5-2 V2, 5-3 V3, 5-4 V4, and 5-5 V5. So this is the equation of current, or how we can write down the current equation for interconnected power system. So if we understand this point, then we can move on to the next part. That is, if we find out the current equation, then now we have to calculate the power equation, actually the complex power equation. Now the complex power injected from bus I, the equation should be Pi minus jQi. This is the complex power format, Pi minus jQi, and the equation should be voltage conjugate into current. So voltage will be the number of bus, that is the I, because we want to calculate the complex power injected from bus I. So that is should be voltage for bus I, Vi into Vi conjugate into current of bus I. And we just derive the current equation for particular bus. So the equation of power, or a complex power equation, should be look like this. This is the voltage magnitude of particular bus I, and this is the current equation, and this is the angle actually. This theta in is the angle of Y bus matrix element. This del n is the angle of voltage Vn, and this del I is the angle of voltage of bus I, and this is minus because the conjugate sign. If we assume that the angle of particular bus I is positive, then the conjugate angle should be negative. So this, for this reason, this is the minus sign. So this is the complex power equation. And if we just separate the real and reactive power from this complex power equation, then the real power Pi, the equation should be voltage Vi into current, and this is the current equation. And we have to consider the angle, the cosine of this angle, because this is the real power, and we know the real power equation is Vi cos theta. So we have to calculate the cosine of the angle. So this is the equation of real power, and the reactive power equation, that is V voltage conjugate into current, and the angle should be sine. So we have to consider the sine angle. So this is the reactive power equation, and here there should be a minus in front of the reactive power equation, and this minus came from here because P minus JQ. So this, if we just change the side of this minus, then the minus should be multiplied from the right hand side of the equation. So this is the in front of the equation. This minus is multiplied for with the whole equation actually. So this is the real power equation, and this is the reactive power equation, and this is the complex power equation for interconnected power system. And we have to remember this real, reactive, or complex power equation for further power flow solution calculation. Now we have to know the different types of buses. So now here there are three buses actually. One is load bus, another one is voltage control bus, or PV bus, or generator bus, and another one is the slack bus or reference bus. So at first we have to know these different types of buses actually. So there are three types of buses actually. Number one, there is load buses. So load bus, or we can write this as PQ bus. So load or PQ bus. So if this is a load bus or PQ bus, then the given value should be, so the given value should be the real power P and the reactive power Q. This value is given because this is a load bus. And for this particular bus, we have to calculate we have to calculate the voltage magnitude. So we have to calculate the voltage magnitude V. So this is the voltage magnitude. So we can write down this this is the magnitude actually. So this is the magnitude of voltage V. So this is the magnitude of voltage V, and we have to calculate the angle actually. So angle of voltage V. So this thing we have to calculate. So now for load bus, so particular bus, or this is the non-generator bus. In a bus which generator is not connected, just load is connected. So this bus is the another name is PQ bus. So PQ means here the given value is real power of this particular bus and the reactive power of this particular bus. These values are given, and we have to calculate the magnitude of this particular bus and the angle of. So for example, if bus 2 is PQ bus or load bus, then the real power P2 and the reactive power Q2 are given actually, because this is a particular load bus. So P2 and Q2 are given, and for we have to calculate the voltage magnitude and angle. So we have to calculate V2 magnitude and angle of V2, So we have to calculate this thing. So for example, if bus 2, so bus. So for example, if this is a bus 2 is a PQ bus, so in our question, real power P2 and reactive power Q2 will be given, and we have to identify the magnitude of voltage V2. So we have to identify the magnitude of voltage V2 and the angle of voltage V2. So this is a particular bus, or we can calculate this is a load bus. Now, if this is a generator bus, so if this is a generator bus, so this is a second type of bus. If this is a generator bus, then that should be PV bus. So if PV bus, then our given value should be P and V. So given value should be P and V. So we can the given value should be P, and this is the magnitude of V. So these are given. This is the PV bus, and we have to calculate the angle of V actually. So we have to calculate the voltage angle. So example, if bus 3 is a PV bus. So if bus 3 is a PV bus, then the P3 and the magnitude of V3 actually. So the magnitude of V3 is given. So the magnitude of V3 is given. So now, well, so this. So the magnitude of V3. So if this is bus 3 is a PV bus, so real power P3 and the magnitude of V3 are given, and we have to calculate the angle of V2. So we have to calculate the angle of V3 because this is the bus 3, so you have to calculate V3. So this is the second type of bus, and this is the second type of bus, and this is the PV bus or generator bus. And now the last type of bus, that is slack bus. This is the slack bus, or this is the reference bus actually. Or another thing, this can be swing bus. So if this is a slack bus, reference bus, or swing bus, then this bus should contains a generator. So this bus should contains a generator, and most probably the large machine of the system is considered as a swing machine, and the connected bus of the large machine is considered as a slack bus or swing bus or reference bus. So for this particular bus, our given value for this particular bus, our given value is voltage magnitude and angle. So our given value should be voltage magnitude and angle, and we don't need to calculate anything for this particular bus at first condition. So if this is a slack bus, reference bus, or swing bus, then in our question, the voltage magnitude and angle will be given, and we don't need to calculate anything for this particular bus. So this is the three types of buses in our power system. So at a glance, if there is a 30 bus power system, so if this is the power system contain 30 bus, and in this power system, the PQ, it means that the load bus is 20 number of bus, and that is the PV, the generator bus, that is the 9 number of bus, and the slack bus or swing bus should be 1. So the slack bus, the number of slack bus should be 1. So for a particular power system, if there are 30 buses, then the load bus may be 20, and the generator bus maybe 9, and slack bus is 1. So one thing you have to remember, that is in this particular power system, non-generator bus is 20 and the generator bus is 10. So in this particular power system, so the non-generator bus so non-generator bus number, that is 20, and the generator bus number, or the total number of generator bus, that is 10. That is 10. So, but within this 10 generator bus, one bus should be slack bus or swing bus. So this is the slack bus or swing bus number 1, and then the generator bus number should be 9, or total number of generator bus should be 9, and the rest of the buses are load buses. So a particular generator bus can contain a load bus. If a particular generator bus contain a load bus or contain some load, then the power generated from the particular bus at first supply the demand of this particular bus. Then the rest of the power will deliver from the particular bus to the other buses. So this is the types of buses in our power system. And for this particular lecture, we can learn the types of buses or different types of buses in our power system. We learn the current and power equation of interconnected power system and the power mismatch equation for interconnected power system.